Now we're looking for two big deal numbers. The way I originally introduced this and the way you've worked on it, what we're looking for is the y factor for which the slope graph has zero concavity. Now, since we're talking about a y factor, we're talking about a power function here. We don't have what we call a y factor. We can get y factors for other functions, but if I say this without further qualification, we know I'm talking about a power function with a constant y factor. And that's what we have originally looked for. And also the base, well, the doubling displacement of the graph for which the slope at the origin is equal to the value of the function at the origin. Now, doubling displacement of what? Doubling displacement of, obviously, an exponential function, because for any other type of function, we don't talk about a doubling displacement, or at least not a consistent doubling displacement. So just like we're talking about y factor without saying anything different, we're talking about doubling displacement without qualifying that in any way. We're talking, in this case, about a power function, in this case, about an exponential function. Now, I'm going to modify that slightly to say really what we want is the power p that's obtained from that y factor. So once we find the y factor, we can easily find the power p. Okay? And similarly, once we found this doubling displacement, we can easily find the base b. So maybe I ought to write b for the base of the exponential function. Okay, well, let's look at what this means. Okay, well, if the slope graph has zero concavity, then we have a slope graph. This is our y prime equals f prime of x, our slope graph for some original graph. That slope graph has to have zero concavity. Now, the only way you can have zero concavity is for the whole graph to be a straight line. The power function, and if the slope graph represents a power function, which we haven't proven, but which we're going to tentatively assume, then the point 0, 0 has to be on that line. So right there is a graph of slope graph. Here is, a slope graph whose original graph is the desired power function. So you might ask, how do we maybe use this to construct this graph? Could be interesting. Okay. Down here, we want the we want to find a doubling displacement that makes the slope at the origin equal to the value of the function at the origin. Now, I'm going to assume that we haven't approached it this way, but just for interest, I'm going to assume that this graph has an equal x and y scale, and I haven't put a y-axis on it yet. Okay? So if the x and y scales are equal, then the slope, well, we know the value of the function at the y-intercept is 1, right? B to the 0 is 1. That's the value at the y-intercept. So we want a graph whose slope at the y-intercept is 1. So if we assume equal scales, the slope 1 corresponds to a line at 45 degrees relative to the x-axis. And that, on this particular graph, occurs right about here. So if I put my y-axis here and assume equal scales, so I'll say if equal scales, that scales on the x and y axes are equal, then the tangent line at y-intercept is at 45 degrees. So locate the y-axis accordingly. So right here, tangent line's at 45 degrees. So the y-axis has to be here. Now, this point has to be 0, 1, which means that 1 is this big. Okay, now if 1 is this big, and if the scales of the x and y axes are equal, then 1 has to be this big down here. So, and we take our compass, construct 1 here, construct 1 down here. It looks like this distance 1 that I'll indicate in a different color. So this arrow has length 1. Well, it's not a good place to label the 1, but let's pretend I've done that reasonably. Okay, if that has length 1, then we just take that arrow and turn it over this way and say, okay, well, 1 goes from, let's see, it's this long, so go from the beginning of this arrow about to the middle of this arrow. Now, I don't guarantee that I've constructed this very accurately, but if you construct it with good accuracy, you'll be able to estimate how many doubling displacements this is. It looks like it's somewhere between 1 and 2 doubling displacements, which means the doubling displacement will be somewhere between half of this, which would be 1/2, and double this, which would be 2. So that's kind of an interesting approach, and y'all have designed other approaches. So, again, our 2 big deal numbers. We want to figure out the y factor up here and use that to find the power p. We want to figure out as best we can the doubling displacement here so that we can figure out the base of the function.